Log on, tune in, find out. Another good idea from Cambridge.
Second talk for this morning is by Jacques Hurtubise from McGill, who's going to tell us about monopoles on a surface cross circle. Okay. So I'll try not to have you fall asleep. Okay, so it's monopoles on the product of a Riemann surface and a circle. So maybe first, why? If you look at recent work of Witten and Kapustin, they reinterpret the on the geometric Langlands correspondence. They reinterpret the sorry. Yes. So if you look at recent work of Witten and Kapustin on the geometric Langlands correspondence, they reinterpret the Hecke transformations that are sort of a vital part of the story in terms of monopoles and scattering on sigma cross an interval. And so in some sense the natural sort of geometric question was to look at the self-Hecke correspondences and see what came out of this. So that's one reason, and maybe another reason which is underlying this. When sigma was a torus, there's a nice Nahm transform to instantons on, I suppose, the dual torus cross S1 cross R. So just as part of just understanding this procedure, and in fact this was the subject that first interested the person I was working on this with, so all this is with Benoit Charbonneau. So monopoles, so well what? Maybe. So what you've got is a unitary vector bundle on the Riemann surface across the circle. So sigma Riemann surface, the usual genus. It's got a Kähler form omega. The circle, well, it's got its usual metric, and its circumference is capital T. So you've got a unitary vector bundle on this. You've got a connection, unitary. And a section of the unitary transformations of E, which are the Higgs fields, and you've got the Bogomolny equation. Now it turns out, in fact, that essentially for the same reasons as those for on a surface, where you don't look at the just the self-dual Yang-Mills equations, but you have the Hermitian Yang-Mills equations. So questions of degree, in other words, you want to look at a more general equation, which, for some odd reason, the name of Einstein got mixed up in it. So Hermitian Einstein Bogomolny equation. So this time you just shift things by essentially a multiple of the so there's some constant C that comes in times the identity transformation of E, plus times the scalar form on sigma is star d phi. So you have to put that in. If there are no singularities, the equations are kind of dull, or the equations might be interesting, but the solutions are dull. The things tend to be, for example, when you don't have this term, things tend to be flat, and the phi is covariant constant. So we have to put in singularities. And in particular, what you end up with, in fact, is not a vector bundle on sigma cross SI, but you have to remove some points. So I equals 1 to L, well, let's put capital PI. So, and what type of singularities are you going to put in? Well, they're going to be basically inspired by the grandfather of all monopoles, which are the Dirac monopoles. So if you look at the Dirac monopole, what you have is if you're on R3, you've got with spherical coordinates, say theta and psi, you've got a Higgs field which is I over 2r times k, and you have to, because the bundle you're on is non-trivial, you have to have a form so I k over 2, 1 plus cos theta d psi on theta different from 0 and a pi I k over 2 minus 1 plus cos theta d psi on theta different from pi. So, so that's the type of thing you want. And so here, well, you're in UN, but what you want basically is that you want at points pi, which I'm going to write as little pi and ti, belonging to sigma cross 0t. So I want phi to be asymptotic to the I times the diagonal over 2r. So there'll be constants ki1 to kin, integer constants. Yes, sort of small detail. K is the degree of this bundle. So k here is naturally quantized, and that's of course why Dirac was interested in the thing to start with. So here the kij are in Z. And you also want, not only that, you want some extra regularity. So this is plus some stuff that stays finite when you approach the singularity. And you want nabla R phi to be also finite. So that's what you want. Just a small comment. I'm omitting the origin, which of course gets identified with t here because that's my circumference. just because it makes life easier. Of course, everything's perfectly sort of invariant under rotation. Okay. So this is the singularities you want, and you're going to therefore choose points. So pi, ti, as we said, belong to sigma cross 0t, and these integers ki, ki1 to kin. And I might as well order them. So and so they're going to be L of them. And I'm going to choose the PIs all distinct and the TIs distinct. So all distinct. Again, mostly it just makes life easier. Though you really do want to keep the PIs different from each other. Okay, so, and you want the moduli space, therefore, of m sigma of the monopoles with singularities of pi, ti's, and of type ki. And what else do you want? Well, what have you got here? You've got t equals 0, and then you're putting in some singularities, p1, t1, and again, I'm going to order the ti's, so unfortunately the other way. P2, T2, and so on. And these are the copies of sigma. If you think of it, what you're doing here, if you have an initial degree for your bundle, so K0, as this plane is homologous to this plane plus a sphere around that puncture, essentially as you move through this puncture, you're going to be changing degree. And you'll be changing it by the trace of ki, which is just the sum of over j of kij. So you'll be adding in, the degrees will change as you move through the singularities. Of course, one of the consequences is the sum of all these things has to be 0 because you want to come back to where you started. So this is the singularity data, and this is the degree at over sigma 0, or sigma, yeah, well, sigma 0 equals sigma prob 0. Okay, so this is the you want the, and this will be the moduli of the monopoles. And I suppose I should put in the rank and things of the bundle, but we'll leave that alone. Okay. So you have, as I said, there's a topology to these things. As you move through, you change degrees. And in fact, there's some constraints. Well, the first is just as I was saying, the sum of the over ij of kij equals 0. So that's just saying that the degree of E0 is equal to the degree of Et, which is necessary for making sense. But there's another rather interesting one, which is that the sum over ij of kij tj is equal to t k0 plus this constant that I had in the equations up there, Cn over 2 pi, the volume of sigma. Okay, so what this means is that the TJs determine this HE constant C. Okay, so that if you didn't have that constant C in the equations there, you're part of there would be a constraint on the location of the singularities. Okay. I should say that this, I mean, this is basically, this constraint is very similar in some sense to Abel's theorem. If you think about it, we're going to see that these things have holomorphic structures, so these are going to correspond to poles of some holomorphic objects. And if you think of the location of poles of a meromorphic function, they're constrained by integrating them against, well, integrating the holomorphic one forms on the surface, well, to the zeros and the divisor, and of course putting in signs. And that has to lie, or sort of lie in a lattice point, or once mapped to the Jacobian, has to map to 0. So Abel's theorem. This is basically the same thing. You've got, if you look at the trace of the Higgs field, it's harmonic, and you sort of integrate it against the function. Well, you integrate the form dt essentially, and you get the same sort of thing coming out. So it's just a remark, and you find that the constraint for building a harmonic function with poles at the right points is basically constrained in the same way as a holomorphic function on the Riemann surface. Okay, so the aim the aim here is you want a well, I suppose, well, you want a Narasimhan-Seshadri theorem, or if you want a Kobayashi-Hitchin correspondence. So you want a relation between these unitary objects and something holomorphic. And so what I want to do is get from a monopole, get to some holomorphic data. If you look at these equations up here, you can rewrite your Bogomolny equations as a first equation, which is just that the fact that the operator, the connection along the Riemann surface, the d bar operator, and dt minus I phi commute. So that's the first one, and then the second is the whoops, get the numbers right. And again, I'll get the i's and factors of 2 wrong. So, well, if you take the curvature and just look at the component along the surface, so contract with the Kähler form, nabla T phi. So you get this equation too. So, and as is usual with these things, this is the holomorphic bit, if you want, and this is the variational bit that you have to solve yesterday to prove this correspondence. So, well, what is this thing? Well, a d-bar operator on a Riemann surface, of course, is always integrable. So you always have a holomorphic structure. On sigma cross T. Okay, so that's easy. But you have something more, which is that if you think of here's sigma, well, let's say sigma T, and here's sigma T prime, and you've got these lines, and you integrate nabla T minus I phi S equals 0 along these lines. It gives it, because it commutes with a d-bar operator, it gives a holomorphic isomorphism. On one condition, that there are no singularities sandwiched in between. Of course, when you don't have I mean, you don't want the singularities on these two sigmas, but you could have a singularity in between, but a singularity in between, well, something bad will happen when you try to go through it. So what happens? Well, what happens at the singularities? Well, if you look at the Dirac monopole, it's just have to change coordinates and so on, and you have coordinates, say z, well, z is badly chosen, so w, say maybe x plus iy, and you go through the origin, you find that the solution essentially behaves like z to the k, or w to the k here. So in other words, nabla T minus I phi S equals 0, S is w to the k, or multiples thereof. So basically what you can see is here, you find that going through a singularity, that your if you want this scattering map, this isomorphism, well, gets changed to you get something holomorphic and invertible, and then z to the ki1, z to the In other words, you get something that can have zeros or poles, and then it gets post-multiplied by something invertible. So these are invertible. And these are singular. So now if you do the obvious thing and just go all the way around the circle. So going around circle, you get rho, which takes you from E0 to E0. And what it will do is it will have singularities at the points pi, and I'll just say of type Ki1, Kin. Okay, I mean it's a theorem, I think, of Iwahori that basically singular meromorphic maps into GLN can be written this way, and there's a sort of generalization for arbitrary reductive groups. So, so your holomorphic data will be pairs E0 rho, where E0 is holomorphic degree K, 0, and rho E0 to E0, oh thanks, sorry, meromorphic with singularities at pi and type Ki1 to Kin. Okay, the singularities, because this is generically a meromorphic isomorphism, the singularities can be zeros and poles. So you have to, and one singularity can mix both. Okay, there's one extra bit, of course, with any of these theorems, which is what's the appropriate notion of stability. So.
Jacques, how does this homomorphic data know where the T's are, or doesn't it?
Stability. Yeah, no, it's whoops.
Also, you haven't told us yet what sort of transformation E goes. You haven't told us yet what happens to E as it goes through one singularity either, have you?
Well, it becomes an E prime, and then if it goes through one singularity, it'll have something that's an isomorphism away from the bad point, and near the bad point, you'll get something like this.
Is this some sort of elementary transformation?
It's an elementary transformation. It's your basic Hecke transformation, but with some multiplicities and stuff.
So there's some sort of flag in a pipe, some implicitly.
Yeah. So it's going to. So actually, maybe I'll just write the stability here, which makes more sense. Stability, well, so if you define a t degree, Ti over t. Of course, we came up with this, and we were talking to Marco Gualtieri, and it shows that some people are smarter. He just said, oh, this is the average degree. Of ET in T. So you just take the average over the circle of the degrees, and that's where this appears, and then you so call this delta T of E. So it's equal to the average degree, and then you have the slope, well, the T slope, if you want, which is the usual thing. So it's the degree over the rank. And then the stability is the usual story of being the slope, sorry. Slope T of E. For, and this is important, rho invariant. F. Okay, so that's the thing. And of course, the aim is to show that this stuff, with the stable ones at least, are isomorphic to these things, to these monopoles. So we've done the transformation one way. You show that a monopole is stable. It's usually the same thing. It's basically the usual idea that if you have subsheaves, their curvature is less, or subbundles, their curvature is less than the bundle they're living in, and therefore you get this stability relation. It turns out actually to be easier in the proof to sort of do things inductively in the rank, just because if you know it inductively in the rank, you can use the theorem, show that it's a monopole, get some nice fields, and sort of play the game that way. But anyway, so monopoles are automatically stable. That's the moral. So we want to sorry. Here. So we want to have the monopoles give you a stable E rho. As usual, if it's irreducible, so irreducible monopoles. And if they're reducible, then you get a polystable object in the sort of standard way. So now you want to get back. Now, I mean, if you sort of look at these things, there's a sort of, by now, the universal theorem is work of Simpson, which basically covers everything well, not quite everything, but it does all the work for you. The only thing is you have to check the T stability is the same thing as Simpson's. And then you're done. Well, you're almost done. Because what you don't have is the nice asymptotic behavior at the poles. So,
What do you mean by almost done? Is this a uniqueness statement that given this holomorphic data, there's a unique monopole?
you can, there's, well, existence and then uniqueness. Uniqueness is not too hard, but the existence is
For
the,
existence and uniqueness.
is the hard one. And what happens basically is that you have to, well, you build, I mean, I'm saying you're done. What you have to do is you build from E and rho an initial condition on sigma across the circle. So you have to build, in other words, a bundle, so you have to extend it, and then sort of, well, extend it first to the interval, then glue it back, and glue it back obviously using rho. Then you have to insert, inserting is your initial condition, essentially just sums of Dirac monopoles. So inserting sums of Dirac monopoles at the singularities. Okay, so you're starting, in other words, with the Dirac solution in the thing. So you've got, in other words, here, and you're putting in your singularities, and on some ball around the singularities, you're gluing in the Dirac, you put in partitions of unity and smooth everything out, and then you've got an initial point, and then, actually, this is, then two, it's basically a heat flow on the metric. So in other words, this is your time zero solution, and so this is the initial condition, and then take, if you want, time to infinity. And that'll be your object in the end. So you'll get a solution. The stability ensures that it converges, except for one thing, which is that don't quite get good enough control at the poles. Now, normally this would be a rather technical thing that would be rather dull, but it turns out there's some very nice and interesting geometry. Poles. So, and it goes back to Peter Kronheimer's master's thesis. Well, probationary thesis, whatever. And what you do is you don't. These basically, Simpson's theorem, the way it works is it's for you want to get onto an even dimensional manifold, so you put in an extra circle, just take the product with a circle, and you've got the Yang-Mills equations on the, or Hermitian Yang-Mills on the 4 manifold. Here you're not going to take a product with a circle, but rather you're going to use the Hopf vibration. Or rather, it's, if you want, it's suspended version from the 4 ball to the 3 ball. So if you have complex coordinates, here you send it to something like, and then 2W1, W2. Okay, and that gives you a map, and it's if you restrict to a 3-sphere here, the 2-sphere there, you get basically it's the Hopf map. And you can lift locally D plus A. Well, lift A phi if you want, or the connection to, this is pi, pi star nabla plus phi times a vector xi, which is or form rather xi, which is 1 over I W1 dW1 bar minus W1 bar dW1 minus W2 dW2 bar plus W2 bar dW2. There we go. Okay, so you do this, and this basically turns the monopole equations and they're into Ricci instantons. But this lift so if you got the Dirac poles here, everything gets smooth. Sort of miraculous. So now this would be if your surface had the Euclidean metric on it, the circle. So in our case, and this was also, I think, developed further by a student of his, Pauli, who did the general case with the analysis. We don't quite follow Pauli's. We sort of put it with a twist on its own, but basically it gets smooth enough, so it gets to a C1 solution. And then what have you got? Well, you have for time, so let's call, we used T already, so let's use S for time, and S equals infinity. On B4, you have here smooth initial conditions for the heat flow. Here on the boundary, you take Simpson's solution, and you replay the film. So you had Simpson's heat flow sort of out here, well, actually extending to the singularity that you have to deal with, but now up on B4 with this twist, now things are smooth here, and so they'll just stay smooth all the way down. So smooth down here, and you reproject. They're smooth up here because you took the Dirac solutions. The C1 business because you then have to sort of modify the equations a bit. Okay. Now, so that in fact sort of settles the theorem. Now, then you can sort of look at special cases, and there are some interesting ones. Well, maybe just a remark. There's a nice spectral curve construction. Of course, you now have a bundle plus a meromorphic endomorphism on sigma. Well, this will give a spectral curve. Say S in sigma cross P1, and what's generically a line bundle, but is more generally a sheaf, supported on S. Okay, and then the algorithm is basically S is the determinant of rho minus a coordinate, let's see, well, say lambda times the identity, where lambda is the coordinate on P1. So S is just given by this equals 0. L is given as the quotient sheaf. Let's see, E minus infinity, rho minus lambda I, L. So you get L as the quotient, and of course, where this is an isomorphism, there's nothing here, but when it is, then this determinant has to vanish. When it isn't, rather, this determinant has to vanish, and so you get something supported on the curve. Conversely, of course, E is the pushdown of L. And if you want, rho is the pushdown in the obvious sense of just multiplication by the fiber coordinate. So, I mean, this is a sort of standard thing with integrable systems. I mean, well, Hitchin and Beauville and various other people. And you notice one thing, actually. This is probably an important thing. If S is irreducible and reduced, so, well, S, yeah. So if there's just one component to S and it's reduced, then E rho is automatically stable. Because there are no sub things. There's nothing that's invariant. Okay, so and that's a rather sort of useful comment when you're actually trying to build these out. Okay, so maybe some examples. Yeah, well, example, maybe if you look at the Riemann surface, so I'm going to set well, I'm going to set just write K here to be the sum over J less than J prime Kij minus Kij prime and the sum over I. Okay. And then the moduli space, you can show that in fact this moduli space is smooth and of dimension 2 plus k in brackets. Not only that, but the Hitchin map for the spectral curve, so the thing that takes E rho to the coefficients of the equation of S is a Lagrangian fibration. So M is a symplectic manifold, in fact, holomorphically symplectic, and it's this is Lagrangian fibration. With fibers that are generically the Jacobians. Sorry? It's, yeah. At least it better be. No, but it is, yeah. That's one of those sort of combinatorial things. It's, in fact, this was, I studied this earlier in a paper with Eyal Markman. Myself I don't trust, but I trust Eyal. So with using this is linked, in fact, to understanding the there's a sort of analog of these R matrix systems, which are sort of generalized Hitchin systems for that live over arbitrary Riemann surfaces. The analog is this Sklianin system, or generalized Sklianin bracket that can be defined, but only when the base is a P1 or a torus. The thing doesn't work for higher genus. And in fact, there's some generalized Yang-Baxter equations. There's a whole sort of mathematical physics story, but the geometry behind it is basically G bundles on an elliptic curve, and then you think of P1 as being a degeneration. So either a nodal or a cuspidal degeneration of the curve. So G bundles and a meromorphic G-valued section. So, and you can sort of do this in general for all reductive groups, but in particular for GLN, you can do it. So the Sklianin bracket. So that's a sort of interesting piece of ties to some which are rather fun.
So the actual statements you wrote on the board don't hold when sigma is not T2.
Well, I don't know it's smooth. There's an analogous thing for the dimension, and it won't be symplectic. It'll be no, not even Poisson. Probably degenerate the other way around. So whatever you call it, symplectically degenerate. Or
Spectral curve story is universal.
yeah, the spectral curve story is universal, but what happens, basically there's a whole story relating integrable systems to at least in the GLN case, integrable systems to Poisson surfaces. And if you look at the Poisson structures on P1 bundles, it essentially amounts then to, once you sort of, apart, K3 is fine, okay, but you get rid of those and you end up with a rather small list of examples which tend to be P1 bundles over a Riemann surface, and P1 bundles with that are the projectivization of a sum of line bundles, in fact. So it's quite boils down. And what happens basically is that you then look at the sort of singular locus of the Poisson structure. And it turns out that for P1, for curves of higher genus, basically the singularity is basically twice the section at infinity. Okay, but P of L plus L prime, one of them has higher degree, and then it's up there. Or lower degree. Well, anyway, I'll sort it out afterwards. For the P1 and T2, there's another case where you can get two sections. And you should really think of, the double section at infinity, the fiber is C, that's additive. Two sections, fiber C star, and that's multiplicative. And when it sort of percolates through all the machinery, basically, the additive thing gets translated into a Lie algebra, and the multiplicative thing gets translated into the group. But it only works for P1 and the elliptic curve. So, I mean, this is sort of metaphysics, but it seems to be borne out in reality. For general, maybe just general sigma, there's a you can show that the generic dimension is G plus 1 plus K. but it's harder to see if it's smooth, and so there's a bit less control. Of course, if non-empty, right? And maybe just a general remark. Is that you can E row is easy to build. Trouble is showing that it's stable. And there in particular, some sort of connectedness for the components, there should be just one component of the spectral curve seems to be the right way. And that you can even do it locally in the sense that if you arrange for your spectral curve to have a sort of n-1 fold branch point, n-fold branch point, then it implies that it's just going to be one component. So you can sort of use that to create connected components. Another sort of trivial remark is that you can show things that exist on an interval. So you've got, say, E here on this piece and E prime here and a bunch of singularities and a row that goes with it. And you'd like to show, you've given E mapping, row mapping E to E prime with some singularities. And of course, then you can just sort of glue in something at the back with a row prime and with a bit of finagling arranged for things to be stable. It'll show you there's one. There's, of course, much more than one. It would be a boundary value problem, probably for the metric. Maybe just one last remark is that tying in with this Nam transform, again, there seems to be some rather nice geometry there. Okay, so you've got monopoles, you've got a Nam transform, which involves looking at the solutions to all possible shifts of the Dirac equation. So on, T2 star cross this one star cross R. So these are metrically the duals of of this, and here you have the complex data map that gives you E row. You have the spectral curve construction. So this is on T2 spectral curve. So you'll have S and L on T2 cross P1. Here, on the other hand, there's a sort of a complex data construction, because if this boundary behavior that you have to impose means that you can sort of complete, basically in the same way you complete this has non-trivial holonomy, but the connection is decaying to a constant at infinity, and you complete it in the same way you'd complete a parabolic unitary structure on a Riemann surface to a bundle on a Riemann surface. So you've got this structure here, and you get a bundle, so I don't know, call it F, on T2 star cross P1. And so you've got a bundle here and a sheaf here, and you can relate these two by a Fourier-Mukai transform, and the rather nice thing is it commutes. So you can do everything holomorphically, or do it the hard way. So it's fine. Thank you very much. Yeah.
So the stability condition seems to be insensible to rescaling the circle. Okay, so if you rescale the circle,
Yeah.
and modify the little TIs accordingly.
Yeah.
It doesn't vary. The 2D equations vary. I wonder
Well,
if
no,
what happens
I mean,
when
it's
the
just on a
circle
different
shrinks.
manifold. Sorry, just taking some sort of limit,
Mathematically,
adiabatic.
like, yeah, making the circle shrink.
Yeah, obvious question. Didn't look at it, so yeah. But it's
Because there are natural equations on the Riemann surface.
yeah. No, I mean these things, of course, have been done, but yeah, no, it's you get. Yeah.
Let me ask maybe a sort of a related question. I mean, have you looked at how the modular spaces depend on the little TIs? Change the structure in the space of
No. I mean, it's sort of the usual, I suppose, this. I mean, in some sense, you see, these, most of them, in some sense, if you've got one smooth spectral curve, then generically it'll be smooth, right? And then everything's stable, because it has to be invariant. So maybe you don't get sort of wall crossings and things like that. It's just most of the stuff is stable.
Also, you mean everything's stable over the smooth spectral curves, but there will be singular spectral curves.
Of course.
It's the same thing one sees with the Hitchin picture, right?
Yeah, I suppose so. Yeah, yeah. But I mean, it's not as if it's sort of a generic thing. It's on a special sublocus of thing. So yeah. So yeah.
Is M hyperkerner a sigma?
Well, this should be. I mean, yeah. But again, more work. Yeah. So.
Is it completely trivial in the case of line bubbles?
All this? You mean, or this?
Well, yeah, just in the rank 1 case.
Yeah, well, yeah, you get a self-map of a line bundle. Well, yeah, no, you get line bundles plus plus a meromorphic function.
Right.
So, yeah, actually, yes, sorry, you can do this, and you get a correspondence with line bundle plus a meromorphic function, and you get a correspondence with harmonic functions on sigma cross S1. And if you sit down and try to design harmonic functions, it's sort of what I was saying about the Abel map and this extra condition of the stability was sort of being very, very closely linked. So yeah, you'll get harmonic functions on P1, on sigma cross the circle.
It seems like if sigma has some special property, if it's hyperelliptic or trigonal or something like that, then you could have a non-trivial spectral curve in sigma times P1, which nevertheless is 1-to-1 over sigma. See what I'm saying?
No, not yet. But saying sorry.
Well, just take the graph of a covering,
Yeah.
large covering of sigma to P1,
Yeah,
right? Then consider that spectral curve.
yeah,
That should give you some non-trivial example, whose existence depends on this special conformal structure on sigma.
yeah,
So might get some special harmonic maps in those cases.
yeah. No, it's
Nick, you had a question?
But does this theory trivialize if the unitary group becomes special unitary?
no. You just get, for example, for SU2, your spectral curve will have an involution. Instead of a Jacobian, you get a prim variety. So from the sort of integrable systems point of view, it's fairly.
You can have these Dirac monopole singularities, but somehow they've got to be traced. I mean,
Yeah, no. Well, you'll have a pole and a zero. Every one will have z to the k, z to the minus k. So, but that's part of the game too.
sorry, just a small technical point. In the top right-hand corner of the central board, I was a bit surprised. So you had del t acting on the section was 0, and you said the section was w to the k. I was a bit surprised it didn't depend on t.
She's to bed. I cheated a bit. No, sorry. I mean, it's like it's basically like this. You can find gauges, etc. The general form is the one I gave there: g to the z diagonal h to the z. So it'll be like that in general, but it's up to multiplication by non-zero holomorphic function. It'll be, well, z or w to the k.
There'll be some t dependence and some coefficient. Probably trivial.
Well, I mean, it's yeah, you have to choose trivialization, but you choose holomorphic trivializations, so you have to choose ones that are in the kernel of the d-bar operator. But that can be, your choice can vary with t. So.
Any other questions or comments? All right, let's thank Jacques.
Okay.